Project Orion was a United States research program to develop a spaceship powered by nuclear detonations, which culminated in designs for exploratory vehicles carrying scientists and explorers to Saturn by 1970. In this demystifying series, we'll look at the history of this ambitious and remarkable venture, as well as where this technology fits into our modern world. An Orion spacecraft is a nuclear pulse propulsion, or NPP, vehicle. This concept is historically the first nuclear propulsion system, and several other types of nuclear propulsion not using pulses were soon developed alongside the NPP concept. Discussions of Project Orion in media today recognize there is an additional body of information the public does not have access to, but which is alluded to frequently in unclassified documents. This cuts short discussions on the finer aspects of NPP, and in this series we will reveal these concepts for the first time. Project Orion began as a concept during work on the first nuclear devices during the Manhattan Project by several of the nuclear era's most influential figures. Dr. Stanislaw Ulam and Dr. C.J. Everett were the first to realistically envision using nuclear energy to propel air and spacecraft, and they published these theories. Ulam was tasked with critical work on fission bomb designs in the Manhattan Project, but would tend to avoid these responsibilities as he developed his more advanced fusion designs. Dr. Ulam was a prolific scientist, often collaborating on ideas with contemporaries such as Dr. Mary Singao and Enrico Fermi. Ulam lectured at major universities over 6 periods, between time spent working at Los Alamos. His life's work spanned nuclear physics, astrophysics, foundational computer science, chaos theory, and biometrics. Mastery over these varied disciplines showed Ulam possessed awareness of many scientific concepts, which aided the formulation of a realistic manned NPP design in the 1950s. At a time where many theoretical developments, such as timing of control of successive nuclear detonations and the affordability of small-scale nuclear testing, would be necessary to confirm his ideas. Ulam worked closely with Dr. Frederick Rhines at Los Alamos, and both have a central role in Orion's legacy. Several scientists, including Rhines and Dr. Frederick Hoffman, had postulated using nuclear energy to power rockets at some point during their work at Los Alamos. Ulam is accepted as the main architect of the groundbreaking paper first analyzing a NPP system, and his contributions would continue as the concept garnered interest. Dr. Rhines, who would be awarded a 1995 Nobel Prize for co-detecting the neutrino particle, discussed using nuclear energy to propel vehicles with Ulam as early as 1946. In 1955, Dr. Ulam and Dr. C.J. Everett would put to paper the first equations resolving the biggest problems of these ideas. Nuclear pulse propulsion quickly gathered attention, and a search for a realistic engine design using current technology and materials was in motion by late 1955. Dr. Wernher von Braun, who was instrumental in organizing early NASA project efforts towards Apollo, had doubts about Orion at first. He quickly reversed this position to being an avid supporter after the first vehicle stability test was conducted. The footage of this test is one of the few surviving video records of the project today. General Thomas S. Power, head of Strategic Air Command, also became a strong proponent for Orion after watching the tests. Nobel Prize-winning physicist Niels Bohr gave his public support to the project, and Arthur C. Clarke repeatedly stressed the importance of Orion, having been informed of the concept through Dyson's publications. Ted Taylor was a close friend of Dyson's, and was a proponent for Project Orion throughout its lifetime. Project Orion's beginnings all involved Ted Taylor, who assembled the work of Los Alamos workers into the formal project and would steer the program throughout its main events. In 1958, Taylor and the founder of General Atomic, Francis Hoffman, both convinced Freeman Dyson to stop teaching at Princeton for a year to come work on Orion. This brief aside from teaching would, as Dyson describes, become the most exciting and important years of his life. Dyson and Taylor led the program's research, although the extent of their specific responsibilities is not public knowledge. While most project details, such as staff numbers, budget, and timeline details, are classified, we will speculate on the organization of Project Orion using evidence and assessing the original Orion documents. Freeman Dyson likely led the project's research and development division, directing all theoretical aspects of the designs. Ted Taylor handled the integration side of the project, assuring the nuclear devices needed could be manufactured, and managed communication with NASA for early testing of the Orion aboard the Saturn V rocket. Jim Nance, secretary to the project director, would take over as director when Francis Hoffman left the program in 1963. The program would continue for 2 more years, but no more steps towards constructing vehicles would be made at this time. At the end of the Manhattan Project in 1939, Orion still consisted of purely theoretical studies. This work by Taylor and Dyson at General Atomics, Nuclear Science Division of the contracting agency General Dynamics, was allowed access to nuclear test and bomb design data from Los Alamos and the Manhattan Project. Much of the theoretical work on Orion continued at General Atomics as the project developed in those early years. The Advanced Research Projects Agency, or ARPA, was created in response to the 1954 Sputnik proposal to begin the development of a competing US space program. It would come into being in 1958. One of the first projects ARPA worked on was Orion, where testing was conducted on small scales. This testing produced the hot rod designs, which proved the vehicle's stability concerns, which were the primary obstacle to Orion's concept. A historical report published about ARPA in 1975 describes how the Orion project arrived at the agency in 1958 and why it was kept limited in scope. A few weeks after ARPA was created, the chairman of the AEC forwarded the Orion idea to Holliday at the DoD, noting that the contractor, General Atomic Division of General Dynamics, had been authorized access to nuclear data to work on it. Before long, the Assistant Secretary for Research and Engineering, the Secretary Special Assistant for Atomic Energy, ARPA, and Deputy Secretary Quarles had agreed to have ARPA support a feasibility study. ARPA supported this work at low levels for several years. It probably served to pacify AEC at a time when it was in DoD's interest to do so, and it probably also prevented AEC or others from making precipitate moves to spend vast sums on the idea prematurely. ARPA's handling of this idea and a number of others had the advantage of 1. Demonstrating that an idea was being looked at professionally, and 2. Prevention of unwarranted expensive systems development." End quote. This 1975 report is being done by an independent source for the benefit of financial and historical records, something we can evaluate today. ARPA was and still is today a specifically focused agency. They develop high-risk, high-value projects. Orion was one of ARPA's first projects and was understandably an intimidating and very risky venture to pursue for the young organization. ARPA intentionally kept Orion a small project, as there were still doubts whether the system would work. This later puts Orion in a puzzling predicament, since the repeated stability tests proved Orion did work, but ARPA would not change its stance in time. By 1960, the agency was shifting away from space technologies entirely and considered Orion even less desirable than before. There are no negative appraisals made of Orion within ARPA's documentation, suggesting its decisions were politically motivated and made chiefly out of financial consideration, which is absolutely standard for an agency like this. At several other points within this document, the actions of ARPA are described as meeting DoD desires in order to secure funding, while prioritizing projects the agency saw as important, which sometimes conflicted with DoD planning. These statements reflect opinions given within the independent report, which are given with surprising directness. There is an apparent intention in 1975 to downplay the role of ARPA in developing Orion, and we ought to recognize this today. Although the Orion program was not a military project under ARPA but a space exploration project, when it began, NASA did not yet exist. When NASA came to be in 1958, the new space agency absorbed many space-related projects from ARPA, but it did not absorb Project Orion, which continued under ARPA's budget. This was the first sign of an untenable long-term situation for Orion, since it was an expansive and costly program, but was split now between space and defense industries, being influenced by military leadership, but with no definite military or defense applications. NASA was uninterested in developing Orion, but it was a large budget item, and it carried with it highly classified designs for small nuclear devices which public agencies such as NASA would have been unable to integrate. NASA would instead focus on Orion's sister project, Rover, for use in an Earth-Mars nuclear shuttle. The United States Air Force accelerated the development of Orion substantially. Through its research management program, the Air Force contracted Project Orion's development plan to Aerospace Corporation. This would produce a 5-year plan to take Project Orion from testing to full-scale deployment. Aerospace Corp was a California-based nonprofit which aided the U.S. Air Force in its development of the U.S. ballistic missile program. Aerospace Corp reviewed planning work done by General Atomics for a 3-year testing plan. They presented their appraisal of General Atomics' timeline with their own 5-year plan to the United States Air Force Technical Area Manager, recommending an increase in funding to fully explore this concept in the planning stage. The Air Force was placing ever greater commitments on Project Orion, calling on the combined efforts of public and private agencies to plan missions. Missions to Mars, Venus, Jupiter, and a permanent Earth-Moon nuclear tug were planned. This Earth-Moon pulse transport idea has been iterated on as recently as the 2000s, with the Medusa concept, which could be constructed in lunar orbit using local materials according to recent studies. Orion would temporarily regain the interest of NASA, who supported a feasibility study for a 20-man long-duration Mars mission. The Air Force's guidance of Project Orion is still largely secret or forgotten. The United States Air Force, through rigorous examination and testing, thoroughly proved the practicality of an Orion spacecraft for military roles. It was through this military-oriented work the mechanized Orion was born. This vehicle could jink to avoid incoming fire and make unplanned trajectory changes at will. Mechanized Orion can produce electrical power from its main drive, another crucial component for a vehicle intended for long-duration missions. But all of these revelations translate into a contradiction. Yes, missions were planned for Orions to visit Saturn and send the next generation to build homes on the moons of Jupiter. But the necessity for military application converted these immense mass budgets to arm vehicles with battleship-caliber autocannons, orbital assault vehicles, and nuclear-pumped lasers instead. When a presentation of the USAF's Orion battleship arrived at President Kennedy's desk, the fate of the military Orion became clear. At a special briefing, Kennedy was presented a report on the status of the program, which promised a strategic asset a century ahead of the current capabilities. An orbital command network of 3 battleships providing line of sight to every location on the planet. In less than an hour, orbital shock troops could be deployed to any location on Earth with nuclear support. Not only was this an inefficient use of money compared to ICBM programs, but it was truly an apocalyptic pursuit. The perspective we have in hindsight of a proposal of absurdly powerful weaponry is separate from the reality of the time. This program had called on the work of multiple public agencies and had succeeded against initial doubts. Project Orion did not have to produce war machines, it was a theoretical study. Designs produced under Air Force guidance were just that, they were proofs of concept, and Kennedy should have known this. There were dozens of lofty projects just like Orion. They continued in order to promote an understanding of physical mechanisms and push the boundaries of engineering. Acknowledging this reality helps us to understand why Kennedy's reaction to the briefing came as a surprise. Those at the briefing said Kennedy was visibly stunned at the proposal laid before him, and went a sleepless night before making moves to ensure the program would not receive further funding. In the scope of the entire project, the President's interactions are limited, but indicative of the final direction of the project. Orion was too entrenched in the interests of the United States science contracting community, supported by influential public officers, military commanders, and renowned scientists. Many of these people didn't just support the program, but had committed their life plans to its success and adoption. The President was the first public officer to decline the Orion, and on a basis that we can guess was mostly political. This situation would eventually lead to the program's death. This situation indicates a complex relationship between the executive branch and public research agencies, something we'll dive into a little bit later. Freeman Dyson, who is remarkable for his strong political opinions on the direction of technology, held strong feelings towards Project Orion's end, stating that, "The story of Orion is significant because this is the first time in modern history that a major expansion of human technology has been suppressed for political reasons." Dyson's words here are more loaded than they appear at first glance, so let's unpack what he means. By invoking the phrase, "the first time in modern history," he is directly comparing Orion in importance to the findings of Galileo and the heliocentric model, drawing a parallel to its subsequent censure by the Catholic institutions of the time. Dyson believed that Orion was a once-in-a-thousand-year opportunity and was subject to contention by political forces. He further implies that Orion is not a tangential technology but a central one, as important as any other modern scientific innovation such as the microscope, the steam engine, the controlled nuclear reaction, or the laser. Dyson is well known for having strong political opinions on the direction of space exploration, so while his assertions towards intentional suppression of the Orion program certainly are worth acknowledging, there are certain reasons the program was deemed non-viable due to geopolitical decisions we can observe in hindsight without adopting Dyson's specific attitudes. Ted Taylor was, as Dyson put it, frequently unrecognized for his work. He, among all of the brilliant minds working on the Manhattan Project, was responsible for designing the smallest fission device ever tested in the United States, the 50-pound M388 Davy Crockett, as well as the most efficient, called Hamlet. He is also cited as being instrumental in developing fusion boosting, a technology that opened the door for nuclear devices with almost no fallout. Taylor is known in science fiction circles for being the first to formally describe the Santa Claus machine, a device which produces any known object out of raw material via manipulation at the atomic level. Ted Taylor is often included in lists of prominent nuclear whistleblowers, having gone on to do widespread public work in developing nuclear safety policy following his years at Los Alamos. He later developed the Triga reactor, a device with incalculable significance to modern medicine. Taylor would spend the latter half of his life dedicated to developing awareness on nuclear non-proliferation, and his earliest ideas on regulating nuclear supply chains are still considered expert and valuable in today's world. When NASA refused to take on the project, Ted Taylor went to the United States Air Force for sponsorship. They agreed to take on Project Orion, and there was a temporary relief that a funding source had been secured. However, a military adoption of the project was the first clear sign of an untenable long-term situation for a complex and expansive space vehicle program. Project head Ted Taylor genuinely believed Orion would succeed, and nothing speaks to this stronger than his contributions. He not only kept the program alive under pressure from government agencies and personal pressure, but would discuss with colleagues the ambition for his own children to fly on the first Orion vehicles on a 5-year mission to Saturn. It was planned that many of the scientists working on Orion would fly on these crafts as civilians, along with hundreds of other civilian and military personnel with widely varying levels of training. Orion permitted commercial spaceflight via 1950 conceptually. In September 1964, the Future Projects Office of NASA's Marshall Space Flight Center published a report in cooperation with General Atomics outlining how the then-in-development Saturn V rocket could be paired with an Orion craft for missions to the Moon and Mars. Note this was 4 years after the Air Force had adopted the program, and cooperation at this point with NASA represented valuable progress for Orion. However, the program was at this point no longer under Dyson's control, and the following year the Orion program would formally end. A need for secrecy which pervaded nuclear programs has left us with a partially complete image of our history. The shadow war of nuclear development claimed a human cost the scale of which we still may not fully understand today. The benefit of these continued tests was often not consolation against the mounting cost and risks to the public. Nuclear testing was being conducted in much the same way it had been upon its inception, as a military program with independence, resources, and goals based largely on pushing the strategic value of the nuclear stockpile. This was a death nail for public perception, since the risk and benefit of these operations for the public are even less attractive. How the public has perceived these technologies is important to the future of NPP vehicles. Nuclear technology used widely in private industries is nearly universally accepted as a positive, but when these technologies include nuclear devices with detonations, there is a clear change in perception. This is partially understandable given history, but also logically flawed in our paradigm today. Nuclear devices have been successfully detonated in recent decades for numerous purposes, being more predictable and safe than equivalent operations using traditional explosives. The Soviet Union used small nuclear devices underground to solve multiple geological problems resulting from oil drilling accidents. Excavation projects were also carried out, and several other nations, including the United States, designed nuclear devices specifically for excavation. One of the greatest issues for Orion and NPP has been the exclusivity of its more technical capabilities. The breadth of these designs, theoretical and practical, produced by the project and by Dyson is extensive. There is tons of data we can see, and even more we cannot. It can be difficult to parse all of these evolutions because so much of the project's history is also likely gone forever. Many of the ideas created by the project's individual visionaries we can only view through the record of publications and interviews they left. This means many creative implications that arise from consideration of NPP have gone entirely ignored, even among modern scientists who have revisited the concept recently. The Orion spacecraft's nuclear pulse engine was so much more than a way to quickly travel around the solar system, and astonishing as its ability to travel was, it was a machine humans would use as a multi-tool to craft the cosmos to their will, building up, sustaining, and expanding installations beyond Earth using mechanisms unique to the NPP design. Before delving into these advanced applications, we'll need to understand the mechanics of nuclear pulses and the discrete interactions occurring during operation. I will go into depth on these ideas in the next part, and I invite you for some of the first public proposals of this technology ever. Some of these ideas are very exciting. As we've learned from the NPP concept, an Orion vehicle utilizes a series of nuclear detonations to impart force to a mechanical pusher system, which pushes the spacecraft forward over brief intervals. We can consider the energy used to propel an Orion starts as potential in the nuclear device used. When imploded, the nuclear cascade vaporizes a filler material, and this filler is the system's propellant. The vaporized filler carries an enormous amount of energy, being accompanied by short-lived fusion and fission products, plasma, as well as intense electromagnetic radiation. The exchange of forces acting within the nuclear pulse-driven spacecraft have separate considerations in contrast to a chemical rocket engine. Enormous energy potential is one thing, but it must be harnessed using known engineering mechanisms. Modern chemical rockets require precise fuel mixtures and pressures and often carry the design concerns of cryogenic systems. This problem of complex rocket engine plumbing has persisted across the history of spaceflight and continues today, where manufacturing offers some apparent recent advances. Manufacturing advances will allow breakthroughs in engine complexity, but only to the degree that the materials used will tolerate. Recall that chemical rockets work by converting chemical energy into kinetic expansion and thermal energy, producing heat, vibration, and forces. All of these considerations represent compounding engineering problems, leading to complex and expensive engine development for increasingly efficient and powerful rocket engines. Compare these concepts to a nuclear pulse propulsion using external pulsed plasma propulsion, where the energy begins not as chemical but nuclear, stored in the isotopes and atomic elements present in the pulse's thermonuclear component. After the detonation of a small conventional charge, the nuclear chain reaction is converted into work by the movement of propellant filler plasma particles and photon radiation pressure. This wave of explosive force can be controlled by altering the fission sequence to take advantage of more photon pressure or more plasma energy, or both, depending on the situation. This means the available energy of the drive is variable without changing the mass of propellants used. The wave of excited particles and electromagnetic radiation does work on the vehicle by impacting the pusher mechanism, which converts some of the applied kinetic energy into potential energy stored in the recoil assembly. The pulsed acceleration of the pusher plate in relation to the rest of the vehicle means the craft maintains a constant acceleration when desired and can increase or decrease thrust output with constant changes in acceleration along the way. Because it can produce constant acceleration suitable as a replacement for gravity, the pusher plate system is a crucial component of the vehicle's suitability for manned use, but you can simplify the NPP engine further by cutting out the structure if high degrees of acceleration are acceptable to the mission. Like chemical rocket engines, NPP engines are configured according to the mission's needs. However, they offer the distinct ability to increase available thrust without changing available propellant mass. We'll get into much more detail on how these engines and their vehicles work later on. Project Orion holds an extremely unique position in our species' history. It may be the single most important technology we have ever acquired due to its potential to expand human presence to the edge of our solar system within our current lifetimes, as well as serving as a tool to construct permanent human space colonies. An Orion can build habitat domes for town-sized populations using a large piece of plain mild steel, using no machinery, in hours or days, and then move them to desired locations in the solar system at will. As incredible as this sounds, it is a feature of having precisely controllable nuclear energy on tap, and this is one of the potential applications of NPP we'll go into depth on later. Key technologies that enabled Orion, such as nuclear weapons and the circuits used in early supercomputers, remained obfuscated from the public until their national security implications were managed. When the public learned of details of the Orion program, it was through the process of declassification, but the academic work of many noted scientists had already publicized the Orion concept. There are a few main ideas we need to evaluate as they directly relate to Project Orion, being part of a larger scientific and political legacy that has resulted in the modern world. Rather than serving as a window into our nuclear development programs, many still describe the ideas behind Project Orion as being fundamentally flawed. This stance can often be found with evident bias, since Orion was always considered realistic and highly applicable by the brilliant minds that interacted with it. Friction is noticeable whenever Orion is brought up, and sometimes fear wins out over reason in public discussions. This is really not surprising at all given the topic though, since even some of those involved in the program, such as the President and Dyson, had strong opinions based on his reservations over misuse of this technology. As we've discussed, these reservations resulted from contradicting objectives being placed on Orion, which stripped the vehicle of its intended mission of discovery and repurposed its shell as a command and control center for all United States military operations on Earth, or even a literal doomsday device delivering retaliatory first strikes using nuclear-pumped laser beams. Today, this is the picture we're given of Orion. A failed, overambitious example of the military industry's strong influence over government and agency affairs in the post-World War II period. However, as we've seen, this is not the whole story, nor is it an accurate depiction of the reality. Orion was the child of some of modern science's most brilliant and influential minds, and retained the interest of numerous entities and advocates until being undermined by the external political realities of the time's global Cold War conflict, something which immediately threatened civilization on Earth at times. Orion had many opportunities to die in a bureaucratic web of US agencies, but instead it expanded in scope every year and gathered supporters among US science communities up until its end. What went wrong with Orion's public perception in the last 20 years? Orion only fully emerged in public consciousness following proliferation of the private internet, where many declassified government programs came under public scrutiny. Some documentary content exists on the Orion program produced in the 90s and 2000s, but their 1-hour format lacks the necessary scope to reveal the NPP's true abilities, focusing instead on pertinent historical events. Prior to these developments, only those with an interest in the activities of fringe spacecraft and interstellar craft, or developments in Dyson's work, would have had any contact with the NPP concept, since Dyson and others published papers about the idea while the project was still active. Human society has chosen to highlight the destructive power of nuclear energy through observable trends and events, and this is an intrinsic bias we have been conditioned to for many reasons. Nuclear power continues to receive mixed press over the incidents arising from regulatory standards and enforcement issues among aging nuclear assets. All of these problems point to issues at the policy level in nations that do suffer from incidents with nuclear power. Suffice to say, our species has a complex relationship with nuclear energy, both historically and today, although the situation has improved drastically in most areas. There is a growing certainty in future-forward communities concerning space exploration today. Humans will need to change their perception of nuclear energy in order to progress. A technology this powerful cannot be limited by indecision if we wish to use these technologies to improve our situation. Project Orion is important because of this reality. We must safely examine and expand the unexplored applications of nuclear energy if we wish to strengthen our position as a participant in the universe, and ensure it is used responsibly in future applications as well. It might sound like I'm describing Orion as a coming-of-age project for our species, for its maturation in handling nuclear energy, and that's partially true. But NPP vehicles are actually not very dangerous to maintain and operate today, particularly in comparison to alternatives. Overcoming our historical experiences with nuclear energy by developing new NPP designs while educating the public on and communicating this process to broad society will help us realize how safe nuclear energy is today by building on the principles we've come to understand since our post-war mistakes. If you're interested, we have more episodes on the way. We also have a mini documentary on this topic on the channel already. I really wanted to go into more detail over this topic. I feel it's a misunderstood and fascinating piece of history. Check out that video and the rest of our content for a grounded perspective on futurism. We'll be releasing this series on Project Orion, continuing our transhumanism series, and we will be bringing even more speculative and historical content soon. Thank you for watching, and please comment and help grow our audience.